So I'm Sidhartha Sankar Roy, a research scholar working under the supervision of Professor Kishore Chandra Biswal in the Department of Civil Engineering, National Institute of Technology, Rourkela. And today I am going to present our trend in this Institute of Research regarding the earthquake resistant structures. Mainly the vibration, earthquake induced vibration, that may be wind induced vibration. That is a matter of context in this different type of engineering fields, especially in structural engineering. So we are employing tuned liquid dampers as a vibration reducer in structures. So these are the contents of the presentation. And coming to the introduction, due to the advancement of construction technology and here in this era of construction of high-rise and lightweight structures, electric structures are increasing in various engineering fields. So due to the higher flexibility and low damping, such structures are severely affected by wind as well as earthquake-induced vibration. So different fields are here. Like building engineering, we can observe that in our well-known building Burj Khalifa, it's also have to bear high-intensity wind pressures, and also in this is a example of this problem in building engineering. And coming to the second figure, this is a wind engineering problem where the windmills have to bear severe air resistance during its motion. And third one is aerospace engineering, where this is the in Tokyo International Airport, and this is the air traffic control tower, where this vibration reducer are being used. So especially in civilian and mechanical engineering fields, different type of vibration control devices are used. So this first one is tuned mass damper, where a building there is a pendulum type damper is there. This one. So this will help this building to resist the vibration. And coming to the second one, this is a base isolation system where the energy of an input energy for earthquake or base excitation will be dissipated by the isolators. And this third one, which is our matter of concern, is the TLD, that means tuned liquid damper, where the inherent energy dissipation ability of the liquid tanks are being used as vibration suppressor. So due to the design simplicity and low maintenance effort, tuned liquid dampers are an efficient vibration control among all these categories, because only what need to be maintained, only the liquid depth, and especially that liquid is our most of the cases it is water only. So it is very economical, and also the main advantage of tuned liquid damper is it can be made over existing structure, because normally base isolator and mass dampers they are to be designed before the structure will started to build, and we cannot modify, and many kind of maintenance efforts are also required. But this tuned liquid damper is a small rectangular or any kind of any shape of tank that can be built over any existing structure. So oscillation of the unrestrained free liquid surface due to any kind of external excitation is termed as sloshing. Sloshing means the oscillation of water. One can observe it from ranging from a variety of examples, like a glass of water. If it is placed over a table and some certain kind of excitation is given to the table, it may be a slosh inside there, oscillate. That is sloshing, and it has an inherent ability to dissipate energy. Hence, tuned liquid dampers are nowadays are very much trend in a very much trending way. So TLD is normally placed near the position of maximum possible modal deflection, which is typically at the top of the structure. Any structure, its maximum possible deflection is always at its top. So at the top of the structure, it is normally TLD were placed. And this is the working principle of TLD, how this liquid damper or a liquid tank works against the vibration. So when the structure experiences an external excitation, the liquid inside the TLD tank responds by out of phase sloshing force. One can observe from this figure, when structure moves left to right direction at a particular time instant, the liquid inside the tank moves right to left direction. So which will induce a hydrodynamic force on the wall of the tank, which will be inherently transferred to its base and acts as a counteracting force. So this is the main principle of tuned liquid damper, how it is suppressed the vibration. It will suppress in the way that excitation and it will be remain in a opposite phase of that. So conventionally, rectangular tanks are normally used as tuned liquid damper, but the one can observe from this figure also the fluid is stagnant at the bottom corners and does not participate in sloshing action, which is our need. So that means we can separate this liquid depth into two parts. One is impulsive one is convective one. So convective means the more oscillatory part that will induce the hydrodynamic force mostly, and the impulsive part remains inactive, does not participate in sloshing, and behaves like a rigid mass. So this non-participating fluid increases the total mass, but does not have any role in the vibration control of the supporting structure. So one can observe that these bottom corners are having stagnant liquid, which will not oscillate, and hence no role in vibration control, because we need oscillatory part of the liquid. More oscillation of liquid, more vibration control will be there, more energy dissipation will be there. So in our scenario, in our study, we are proposing a tank with modified bottom geometry with sloped walls, so that the this stagnant portion will be removed. So what will happen? The convective part will remain the same one, means the oscillation part will remains the same, and the impulsive part where the liquid are gathering will be reduced. So this type of TLD are we are studying. So objective of this study is to numerically simulate the higher vibration control efficiency of the sloped walled TLD. Sloped wall is the name of that tank, maybe trapezoidal one also. But the wall configuration is modified, so hence it is we are telling it like a sloped wall TLD. And okay, so now coming to the mathematical formulation. So uh, the governing equation of motion inside the tank can be expressed as the velocity potential based 2D Laplace equation. And this is the configuration of the sloped wall tank and the boundary condition, the liquid depth, everything is here. Now we are using finite element method to analyze this type of tank. So finite element discretization is like this. We are using 4-node quadrilateral element and 3-node triangular elements also to discretize the liquid zone near to the sloped wall portion. So this is a combination of these two type of elements, and by transformation and rearranging and by applying boundary condition to the governing equation, the well-known, it will take the picture of the well-known dynamic equation, where this mf phi double dot cf phi dot kf phi is equal to force. It is the well-known dynamic equation, but it is solving the sloshing problem. So the elements of the matrix are mf is the free surface matrix, and cf is the damping matrix, and coming to the kf, this is liquid coefficient matrix. And the free then solving this equation, the free source amplitude eta and hydrodynamic pressure P can be observed, can be obtained by this expression. And finally base shear force, which will act as the opposite to oppose the excitation, can be calculated by integrating that pressure over the wall of the tank. So this is the TLD structure formulation, means to interact the motion. So this is a lump mass model. When structural motion, when structure subjected to external excitation, it will respond like that, and when TLD will be placed over that, it will respond in an opposite sense, which is hydrodynamic base shear, and this opposing force will balance each other. So the equation of motion for the structure TLD system can be given by this expression, where one can observe that this is the inertia force of the building, ms x g double dot, means ground acceleration coming, means if let us take a case of earthquake, where ground acceleration will come and it will be multiplied to the mass, and it will act as inertial force of the structure, and which will be balanced by the FTLD, and this one is the base here coming from the TLD tank here, this one. So coming to a numerical example, we are developing our own MATLAB code based on finite element model, and the coupled equation is solved by numeric beta average acceleration method. So this is the validation of our model. The accuracy is validated with the existing experimental results, which is found in a good agreement. So one can observe that this one is the existing one by Gatterson et al, and we are confirming it by this presentation, this figure. And next, coming to the example, we are also validating our interaction model, because this one only for the tank, and this is for interaction. That means structure will be there, and there will be a TLD over that structure, and the interaction we are also examined. So F sin omega t, A sin omega t force will be act, and story force will be act like this, and the response coming are plotted over the existing result, and which is found to be in a good agreement. Then design parameter for this TLD, tune liquid damper. So mainly four things one to be, this should be noted down. The fundamental sloshing frequency must be appropriately tuned to the fundamental frequency of the structure to maximize the performance of TLD. The name tune liquid damper shows that it is tuned to something. Tuned means it will be tuned to the fundamental frequency of the structure. So same sloshing frequency, the oscillation oscillating frequency of the liquid and the structure frequency must be matched to get optimal vibration control. Then tuning ratio, this presented as the ratio of the fundamental sloshing frequency to the fundamental frequency of the structure, beta R. Then the maximum mass ratio, because mass ratio is the important aspect, because let us consider one case, structure is 5000 kg and we are placing a 1000 kg of water tank above that. So that will definitely affect the modal property of that structure. So there will be limited, there should be a limitation, and that is less than 4%. Means the liquid tank, which will be employed as the tune liquid damper, must contain a mass, a liquid mass less than 4% of the total mass of the structure. So that mass ratio is, can be represented as gamma R. So this is a representation of relation between liquid height, weighted perimeter, and fundamental sloshing frequency. This for the left one, A is for rectangular tank and B is for the modified tank, that means slope dual tank. So this is for a ground supported tank. One can observe that the peak hydrodynamic response of a ground supported slope dual tank with 4.08 kg less liquid mass is higher than the conventional rectangular tank. That means the base here near the resonance is higher in case of slope dual tank as compared to rectangular one. But one should note that the water is 4.08 kg less. So with less liquid mass, higher base here is observed in case of this modified damper. So this is a comparison between the rectangular and slope dual tank, whether it is performing better or not. The same structure is taken with 2% damping, and this is the K and mass values, stiffness and mass. This is a rectangular tank, this one is slope dual tank. And it is given, we are giving a sin omega t means sinusoidal excitation. So the same 4.08 kg less liquid mass is considered here. And this is the dynamic response of the structure with rectangular and slope dual tank. One can observe that a structure without any kind of damper is experiencing more vibration, because this is the maximum displacement, this is the frequency, at its resonance frequency, because the structure having fundamental frequency of 0.5 hertz. So there at resonance maximum displacement is occurring, whereas when TLD is equipped, that is reduced. And one can observe with slope dual tank better vibration control is observed here, because here the green one is less. So for both cases, beta is same, means the tuning ratio. And however, a reduced mass ratio is observed. Means for rectangular tank, one can observe from this table, our mass ratio is 1.14, where for slope dual tank it is only 1%. That means with less pressure over the building, we are getting better vibration control, because if additional mass will be there, then will be additional weight over the building or structure. So this is the implementation of multiple slope dual TLD. Means we are because in the previous slide I have shown that it may be up to 4% or 3%. So only 1% mass ratio we are considering here, but we can increase the number of TLD also to increase the vibration control. So when 1% for one TLD, that means 2 is for 2% mass ratio. 3 TLD may be up to 3% mass ratio, and it is allowed. Not we are using up to 3%. So one can observe that without TLD, this is the response. With one TLD, then 2 TLD, 3 TLD, it is reducing gradually. And more than 3%, 4% we cannot use, because that is the limitation of mass ratio, and beyond that it will affect the structure's modal property itself. So this gamma is kept at 1, 2, and 3% for single, 2, and 3 TLD respectively. And this is the time history plot for without TLD and with TLD, 1 TLD and 2, 3 TLD. One can observe that this is a resonance response under harmonic excitation. A 30-second time history plot is shown, where the displacement of structure is more when there is no TLD, without TLD, and with 1 TLD it is reduced, and 3 TLD it is more reduced. So coming to the seismic response, these are the harmonic responses we have discussed, and now it is coming to this seismic response. One can observe that earthquake may be classified on the depending upon its source to site distance. Means if there is a focus of earthquake, and this is the epicenter, and this is the fault, and these are the structure or maybe recording station. So if that is within 20-kilometer range, then that kind of earthquake will be near fault type. And if higher than 20-kilometer, means this may be at this place or this place, then it may this same earthquake may be classified as far fault earthquake. So we are studying the influence of near fault and far fault earthquakes on the vibration control efficiency of that type of TLD, the special type of TLD. So these are the two real earthquake ground motion data. One is San Fernando and one is Cape Mendocino, and these two are scaled to a 0.2 G. That means a scale to a particular acceleration value, so that we can compare the results. So with allowing this two type of excitation to the structure, these are the responses. That means this is the displacement under San Fernando earthquake, and this is this one is the near fault. San Fernando is the far fault record, and this one is the near fault record. One can observe that the structure is more vulnerable to this near fault records with higher displacement. And also one can observe the effects of the tuned liquid dampers here. This is 1 TLD, then 3 TLD. With increasing number, it is reducing, because the green one is more controlled response. These are the peak responses here. This from this plot, this is the peak one, this is the peak one, and this is well mitigated by the application of the TLD. And this is the story shear versus deformation plot for the seismic response. One can observe that from far fault record, we are getting a lower story shear, and also this story shear is reduced with using this TLD, tuned liquid dampers. And from and for near fault record, this is much more higher than that, because near fault record means it will nearer to the fault zone and having some high velocity pulse that will affect the structure more. Even with particular damping arrangement, some structure may fail during this type of earthquake. So these are more vulnerable. So we are focusing our study on this. These are the reducing effects. When one can observe the length is reducing, means vibration control is there. So coming to the remark, near resonance, the sloped wall tank with less liquid mass generates a higher base shear force compared to the conventional rectangular tank with a higher liquid mass. And even with a less liquid mass, that means lower mass ratio, the sloped wall TLD has a higher vibration control efficiency compared to the conventional rectangular tank or maybe cylindrical one. Cylindrical and rectangular tanks are more in use in the currently existing structure. Where the TLD is being used, mostly they are rectangular type or cylindrical type. And coming to the third one is the near fault record are more vulnerable to the structure. As we can observe from this plot, the response is higher under near fault earthquake. And the fourth one is compared to a single tune liquid damper, an efficient seismic control can be achieved with multiple TLDs. Means instead of using only one TLD tank, one can increase up to 3% or 4% maximum, and increasing number of TLDs will definitely reduce the vibration more, because some in some practical example, if we will consider some in Japan or Taiwan, there they have used a single TLD only, but after that they installed more, then increasing the mass ratio up to 3%, maybe sometimes that is 5% also, and that is found to be more effective as compared to single one. And sometimes that may affect in a negative sense also, because in some studies it is observed that increasing the TLD numbers will increase the mass, and if additional mass is there, there will be some change in the fundamental frequency of the structure. If that change in fundamental frequency of the structure will close to some dominating frequency of any kind of earthquake, that may have a negative impact also. If coming closer to the dominating frequency, then definitely the response will increase instead of decreasing. So that may be, that also be a good observation from some good studies, that they are showing the negative influence of this also. But in current scenario, in high-rise structures, they are more flexible, and so having the fundamental frequency very low, less than 1 Hz also. And there, this type of vibration suppressor are more effective as compared to low-rise buildings. Because if low-rise building, your fundamental frequency, if it is greater than 1 Hz, then TLD cannot be used, because sloshing frequency of the liquid is normally less than 1 Hz. It cannot be more than 1 Hz, and it will not effective. So in that case, base isolation system is a good one as compared to this one. So this is only applicable for more than, I think, around 4 or 5 story building, more than that. And if a structure is, or a building is below 6 story, their base isolation system may be used, or any kind of viscous damping system can be used. So these are the remarks, and these are the references of the presentation. Thank you. We can discuss if any question, any query from the audience. We can.
Audience can ask questions to Sidharth. I have a question.
Sure.
What do you mean by convective? What do you mean by convective, and how do you differentiate that from the other part of the water, the one which was like, which
Okay,
was
sir.
not
Okay, sir.
moving?
Sir, whether the slide is visible, sir?
Oh, yes, yeah.
Yes. So actually, sir, convective and impulsive are two
Impulse.
theoretical depth of a particular type of tank. If the total height of the liquid is like this, from this to this, it may be divided into two parts: convective part and impulsive part. Convective means the more oscillatory part. That means those portion of the liquid mass which participates in sloshing. That means more dynamic one. And normally it is closer to the surface of the free surface. And below that level, another level will always be there, which will never move. It will behave like a rigid body, and it will not create any hydrodynamic force also. And that part is known as impulsive one. And the liquid mass inside that layer, it is known as impulsive liquid. And the liquid mass inside that layer, convective zone, it is known as convective liquid. And the overall hydrodynamic performance of shallow water tanks are dependent on this convective one, because the impulsive part will not in a motion, they will like rigid one only. In the bottom corners they are stagnant one.
Oh, so what you're saying is that the impulsive part will have only inertia. Means,
Yes, inertia, yes.
there it will have only inertial force will be there, and
Only,
hydrodynamic
yes.
part somehow it will exert some pressure.
Yes.
How do you differentiate this inertial force with the hydrodynamic force?
Yes, sir.
Is
Actually,
this hydrodynamic force dependent on the acceleration of, is it related to mx double dot, or is it something else?
no, sir. Actually, hydrodynamic base here we are calculating. That means the liquid force at a particular time instant. We are taking. Let us consider the time instant delta t. So there will be a pressure in both walls, both side, left and right wall. Then the algebraic that difference will act at its base. We are assuming that that is the base here of the tank. So we are calculating like each we are discretized this liquid domain into several small finite elements, and the zone closer to the wall we are calculating like that. We are distributing the pressure at each node, and that will be summed up and it will be acted base here. So some portion of the impulsive part also giving some pressure, and but that is very minor. More of the most of the hydrodynamic participation is coming from this convective one for shallow water tanks. Means the if the depth is less, if depth is more, mainly like cylindrical one, there will be more impulsive part and very less convective part.
So you had to do a fluid mechanics simulation to find the convective part. It's not just mx double dot, some kind of a fluid dynamics
Yeah.
equation you had to use, I think.
Yes, 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 sir. We have to. We are assuming the at base there will be no flux condition will be there, and there will be a particular boundary condition. From that, we are calculating impulsive one. Then from total base here, we are deducting that one, to which will give the convective response.
Okay, then let's all thanks Sidhartha Roy for his wonderful presentation about tune liquid dampers for mitigating earthquake response in buildings. We wish him success in his PhD work, and also for post PhD job search. Uh,
Thank you,
Thank
sir.
you.
Thank you for
Thank you,
the
Siddharth.
this, yes, sir, opportunity, and sorry for this interruption in between, some due to some technical errors. Okay.
It's okay. We'll end the meeting, and we'll meet tomorrow at 3:30 p.m.
Okay, sir. Okay. Thank you. Thank you. Thank you all the
Thank you.
participants. Thank you.